Welcome back to video 2 of chapter 12. We're talking about states of matter. So when we talk about our states of matter, we have to remember our intramolecular forces, and those are inside the molecule. These hold the molecule together. So last semester we talked about ionic compounds between a metal and a nonmetal, cations and anions. We talked about covalent compounds between nonmetals where they share electrons, and we talked about metallic compounds where you've got the metal cation and the mobile electrons. So in all of these are inside the metal, and the intramolecular forces are super strong because they hold the molecule together. The opposite is when we talk about intermolecular forces, and an intermolecular force is between two or more molecules, okay? Depending on how attracted they are to each other, makes certain things be solids, certain things be liquids, and certain things be gases at the same temperature. There are a lot of different types of intermolecular forces, and you're going to need to know those. Remember, INTER means between two. INTRA means inside. Okay? So, our intermolecular forces are between two molecules, not inside a molecule. So, our first intermolecular force is a dispersion force. These are super weak, and they only happen when you have a temporary shift. These are found in what are called nonpolar molecules. So, remember when we use the electronegativity, if they have the same electronegativity or very close to each other, you're going to have dispersion forces. Another type of dispersion force is going to be intermolecular force is going to be dipole-dipole, and that is between oppositely charged regions of polar molecules. So remember, polar is when the electronegativity difference is 0.4 to 1.7. That's going to be where you have the positive side of that molecule is attracted to the negative side of a different molecule. And then you're going to have hydrogen bonds, and hydrogen bonds are a special dipole-dipole attraction, so you've got the positive attracted to the negative of a different molecule, and it's anything that contains, you guessed it, hydrogen. Typically it's going to be hydrogen with fluorine, or hydrogen with oxygen, or hydrogen with nitrogen. And it's where the hydrogen of one water is attracted to the oxygen of a different water. So when we're talking about hydrogen bonding, it has to have hydrogen in it. Water exhibits hydrogen bonding, methane exhibits hydrogen bonding, ammonia exhibits hydrogen bonding. So these blues are going to be attracted to the other element of a different molecule. Because of this, they're going to have very odd boiling points, even though they have fairly low molar masses. So what's the strongest? Your intramolecular is stronger than your intermoleculars. Ionic bonds are the strongest, covalent bonds are next. In here, I would add metallic bonds. Beneath that would be your hydrogen bonds. Those are the strongest of your intermolecular forces between two different atoms or elements. Your dipole-dipole, which are the permanent charges that are attracted to each other, and your dispersion forces. So, we've got our three intermolecular forces, our dipole-dipole, dispersion forces, and our hydrogen bonds. The stronger the intermolecular force, the more solid something would be. That's important. I'll say it again. The stronger the intermolecular force, the more solid something will be. So when we're talking about a liquid, it's got more intermolecular forces than a gas does. And that's because they are more attracted to each other. They're going to be closely packed in a fixed volume, but not in a fixed position. So that's for a liquid. Liquids are much denser than gases because they have stronger intermolecular forces holding them together. Gases are not very dense. And you can't really compress a liquid. Remember, you can compress gases because they have lots of empty space between their particles. Liquids are much denser, going back to this right here, because they're much denser, you can't pack them very easily, so they're not very compressible. Liquids are also able to flow and to diffuse, since, fluidity is the ability to flow and to diffuse. Liquids are fluids. Gases are fluids because both flow, because they both have that not fixed position. So fluidity is the ability to flow and to diffuse. Viscosity is the measure of resistance to flow, and is determined by the type of intermolecular force, the size and shape of the particles, and the temperature. So water has a very low viscosity. It has a very low resistance to flow. Syrup has a kind of low viscosity. Molasses has a high viscosity. It is very resistant to flow. Also think about when it gets cold outside. When something's cold, it's not going to flow as easily. So your ketchup bottle, you're going to probably warm it up a little bit to get it to flow. The stronger the intermolecular attractive forces, the higher viscosity. So think about it this way. When the particles slow down because it's colder, they're going to be more likely to stick together, so they would have a higher resistance to flow. I'll say that again. The colder it is, that means that the particles have less kinetic energy. They are going to be less likely to move as fast. Since they have a lower kinetic energy at a lower temperature, they're going to stick together more. That means it's a stronger intermolecular force, so that means it's going to have a higher viscosity. The other thing is large molecules are going to have a higher viscosity just because they're bigger and it's harder for them to flow. Long chains, large molecules, are going to have a higher resistance to flow. And if you heat something up, that decreases viscosity. Because when you heat something up, you're adding energy that allows molecules to overcome intermolecular forces, and they can flow more freely. So, high viscosity, low temperature. Low viscosity typically is going to be brought about by a higher temperature. So we're talking about surface tension. Surface tension is still going around with liquids, and that is where you have an inward force that must be overcome to expand the surface of a liquid by a given amount. So, if this is a water droplet, this is the force that comes from inside. And, okay, we want to pull it apart, but what's also happening is a force that's holding it together that gives it its spherical shape. So, when you have water droplets, those are spherical. So, to overcome that inward pull, you would have to break the surface tension. This is why spiders can walk on water sometimes. It's because water is weird, and water has a really high surface tension, so it doesn't want to break apart. You have to use what's called a surfactant to lower the surface tension of water. So if you look at this right here, the water, if each of these red spheres represents a water drop, it is more likely to want to be next to water than to want to be next to something else. So you have to put a surfactant in it to lower water tension. Also, these are two definitions, cohesion versus adhesion. Cohesion is the force of attraction between identical molecules, while adhesion is the force of attraction between different molecules. This is why they're called adhesive band-aids, because they are attracted between the bandage and your skin. So if something is cohesive, that means it's more attracted to itself. If it's adhesive, it's more attracted to something else. So when we're talking about this, we're going to use cohesion and adhesion to make sure that capillary action, which is the movement of liquid in a narrow cylinder. So the substance in that narrow cylinder would rather be with itself, so it would rather be cohesive. That's why it would move into the narrow cylinder, because it wants to stay with its buddies. So if you look at these drawings right here, water molecules, water is adhesive. That's why water in the graduated cylinder curves down, Okay? Because right here, these molecules want to be next to the glass. But mercury is cohesive. And that's because you're going to have these mercury molecules that would rather be next to themselves or next to identical molecules rather than be near the glass. So they're going to be cohesive to themselves. They would rather be next to themselves when they're cohesive. I remember that. They cooperate. So now we're going to switch gears and talk about solids. Solids have very strong intermolecular forces. While their particles are still moving and still have kinetic energy, they mostly just vibrate in a fixed position. And solids are typically more dense than liquids, with the exception of ice. Ice floats. It's weird that ice floats. And we will talk about that a little bit more in class. And answer the question, what would happen if ice were more dense than water? But ice is not. It's an anomaly. But most of the time, solids are more dense than liquids because of those really strong attractive intermolecular forces, hydrogen bonds and dipole-dipole. There are a couple of different types of solids. We're going to talk mostly about crystalline solids, so that's anything with atoms, ions, or molecules in an orderly geometric shape. The unit cell is part of a crystal lattice, and it's going to be the smallest arrangement of atoms. And then we also have amorphous solids, and these are where the particles are not arranged in a regular repeating pattern. And these are typically formed from molten material that cools quickly, so things like igneous rock or glass, rubber, plastics. So thanks for watching, and that was video 2, where we have talked about these different types of amorphous solids, which are our allotropes, and our covalent network solids, where you've got these big molecules, and these are going to be crystalline. So now we've actually reached the end of video 2. So if you see, this is what a crystalline solid would look like, where it's very geometric and very rigid. And so here are different types of solids, and these are all crystalline. So thanks for your attention.